Just welcome to RTBLive here. And I'm going to, well, just give you a couple personal remarks. I mean, people would ask me questions on Facebook and Twitter, how I'm doing. I mean, I am older in a high risk category, so I've been hunkered down in our home, but it's been a blessing not having to travel back and forth to the office or all across the country or other countries. I've actually had more time to write. And so I've been doing a lot of writing, articles, white papers, also working on my next book, Interior Designs. Already got 8 chapters done in that book. So when that book comes out, I'm going to definitely have to give COVID-19 an acknowledgement because without that, I probably wouldn't have been able to make my deadline. So that's how my life has been going. My wife also has been working. One of the things we notice is that we're actually working more now with this because we're always available, and so we just looking forward to getting back to the office where we don't have to undergo quite so much work pressure. But it's been good. A lot of good things have been happening. Well, I just want to encourage all of you that this is going to be a very slide heavy talk. And if you want to download the slides, you can get those slides at reasons.org/Ross. That portal will also get you free chapters of my books, including my latest book, Weather and Climate Change, giving away chapter 14 of that book. Just for anyone who goes to reasons.org/Ross. You can tell your friends about that as well. And we're going to be showing you the slides in my talk. This is the first slide, which basically just shows you all the ways you can communicate with us while you're in lockdown here with us at Reasons to Believe. Every scholar at Reasons to Believe has a Facebook and Twitter page. And if you don't get to ask your questions today or in the extra feature we have where we're going to pick up extra questions, you can ask questions on Facebook and Twitter, not only of me, but of other scholars. And you may not be aware of this, but Reasons to Believe has a 24/7 YouTube channel. You can subscribe to that. When you do, you'll be notified of when we're loading up new videos, and we're putting new videos up almost on a daily basis. So take advantage of that. And again, you go to reasons.org/Ross, you can get a free chapter of Weathering Climate Change. And a lot of what I'm talking about today comes out of our book, The Creator and the Cosmos, the 4th edition. You can likewise get a free chapter at reasons.org/Ross. However, most of what I'm going to be talking about today is not in The Creator and the Cosmos. It will be in my next book, Interior Designs. So this is a lot of new material. It's never been presented before. In fact, this talk, A Galaxy Like No Other, this is the first time it's been presented. And usually when I present a talk for the first time, it's quite rusty and needing of a lot of revisions and tuning up. So I'd appreciate any suggestions that you might have. Now, any of you who've been to movie theaters over the past 50 years probably have seen this in an opening of a set of films a long time ago in a galaxy far, far away. Every Star Wars movie opens up with this little snapshot showing distant stars, and then this blue type comes barreling out at you a long time ago in a galaxy far, far away. I've been telling our staff at Reasons to Believe they need to edit those Star Wars movies because there is no galaxy far, far away that we've been able to find that's a possible candidate for advanced life. My peers have been searching for decades for a galaxy sufficiently like ours that it could be a candidate for advanced life. And what we've discovered is not only are we living in a galaxy that's unlike any other galaxy, we're living in a super galaxy cluster that's unlike any super galaxy cluster. And we're in a galaxy cluster or a group of galaxies that's unlike any one we see. So I'm going to begin with that. And the first slide I'm going to show you, this is Abell 1300. It's a typical cluster of galaxies, including thousands of galaxies. Virtually every image you see here, matter of fact, as I check, yes, every single image here is not a star, but a galaxy. Ah, I see one star. Just one star, the rest of it's all galaxies. And this is typical of galaxy clusters, where you got thousands of galaxies jammed quite tightly together. And what you see usually in the core of the galaxy cluster are several supergiant galaxies. And incidentally, we're only looking at the core of Abell 1300. It actually has way more galaxies than what you see here. But for example, we look at the super galaxy cluster Abell 2744. This again is the core, but it shows you that often we see the galaxies are even more tightly jammed together. And in this case, they're actually distorting one another's galaxy structure to a considerable degree. And all those fuzzy spots there are supergiant galaxies, galaxies much larger than our Milky Way galaxy. And then here we're looking at a fairly new discovered cluster of galaxies, MACS 0416.1 minus 2403. Don't you love the way astronomers come up with names for the things that they discover? But here you see again the core of this galaxy cluster. Now, the next slide I'm going to show you is our super galaxy cluster, the Laniakea super galaxy cluster. And the first thing you notice is how differently shaped it is. I mean, it kind of looks like a running dog. Whereas what you see in other super galaxy clusters, they tend to look like a sausage or a football or some kind of like a flattened basketball, where you literally have tens of thousands of galaxies jammed all together in a tight little group. What's unique about the Laniakea supercluster of galaxies is that the galaxy clusters are spread out along these long filaments with giant voids in between. And what you see over to the right is the Centaurus cluster, and then just to its left, the Virgo cluster. These are two galaxy clusters that are typical of galaxy clusters in the universe. But notice all the other clusters in the Laniakea supercluster are quite a bit smaller than the Centaurus and the Virgo cluster. That is atypical. The Virgo and Centaurus are typical, but the Laniakea supercluster has all these smaller galaxy clusters. And actually, as we zoom in, we see that as we get close to our own galaxy group, uh, we actually see that the galaxy clusters begin to become smaller. Actually, as you go in the Laniakea supercluster, the closer and closer you get to our local group, the smaller the galaxy groupings are. But here you see the nearest cluster groups of galaxies. That little yellow arrow there points you to the Milky Way galaxy. And that little white spot you see to the upper left, that's the Andromeda galaxy. And if you've got fairly decent resolution, just to the left and below of the Andromeda galaxy is the Triangulum galaxy. And none of the other galaxies in the local group show up in this particular image. But it reveals to you that in the Laniakea supercluster, the smallest galaxy group is the group that we're in, what's called the local group. But it's actually on one of the major filaments of the Laniakea supercluster. And that's a characterization of the Laniakea supercluster. You've got these filaments or strings of galaxy clusters and galaxy groups, and then you got giant voids in between. So we're not on a void, we're actually on one of those filaments. And as you can see there, we're kind of sandwiched between the Mafia group and the Sculptor group. That's our local group. Now, the next slide shows you a to scale map. This is something we produced at Reasons to Believe. You won't find this anywhere on the internet, but you will find maps, but they're not to scale. We made this one to scale, where basically the separations between the galaxies are real compared to the size of the individual galaxies. And this points out what's so special about our local group of galaxies. There are no supergiant galaxies in the local group. You've got two large galaxies, the Milky Way and the Andromeda galaxy, and then you've got five reasonably large dwarf galaxies. Incidentally, the Triangulum galaxy is not the biggest. The biggest is the Large Magellanic Cloud that's just below the Milky Way galaxy. You got two reasonably large dwarf galaxies to the right and left of the Andromeda galaxy, the Triangulum galaxy, and the Large and Small Magellanic Clouds. All the other galaxies in the local group are small dwarf galaxies, and astronomers have now found over 100 of these small dwarf galaxies. But again, I want you to notice how far apart Andromeda and the Milky Way are. Radically different from what you see in other galaxy groups and clusters of galaxies, where especially the larger galaxies are jammed tightly together. Here we see that the Milky Way and the Andromeda galaxy are spread apart. Now, we often referred to the Andromeda galaxy as our sister galaxy, and it is a spiral galaxy of about the same mass as our Milky Way galaxy, but there's substantial differences. And what astronomers have discovered in the past couple of years is that the Andromeda galaxy is a typical large spiral galaxy. It's not a giant spiral galaxy, but it's a typical large spiral galaxy, and the Milky Way stands alone. It's atypical. And so in this next slide, I show you the different characteristic features of the Milky Way, that's that one off to the left, compared with the Andromeda galaxy to the right. What you see is they have about the same mass. Matter of fact, given the error bars, we see no difference in the mass between the Milky Way and the Andromeda galaxy. The best measurement puts the Milky Way at 1.2 trillion times the mass of our star, the Sun, whereas Andromeda comes in at 1.3 trillion times the mass of the Sun. But the error bar in both cases is about a little bit less than 0.2 trillion solar masses. Now that's the total mass, and here I try to break down the mass. The stellar mass, that's the mass of the galaxy in the form of stars. And lay people often think that most of the mass of the galaxy is in its stars. That's not true. As you see here, for example, with the Milky Way, 54 billion of its total mass is in the form of stars. So only a small percentage of the total mass. We're talking, less than 5% of the total mass of the Milky Way galaxy is in the form of stars. Quite different with the Andromeda galaxy, where you get a little more than 10% in the form of stars. So unlike the Milky Way galaxy, it's got about twice as many, it's got twice as much mass in the form of stars, 110 billion compared to 54 billion. And where the Milky Way again stands alone is in the size of its dark matter halo. It's got an enormous dark matter halo. And this just got published literally a few weeks ago, the first measurement of the extent of the Milky Way galaxy's dark matter halo. Its diameter is 1.9 million light years. Now, Andromeda's got a fairly big dark matter halo as well, but it's only 0.9 million, 900,000 light years. Now, to put this in perspective, the diameter of the disk of the Milky Way is about 110, 120,000 light years, but its dark matter halo measures 1.9 million light years across. And so what characterizes the Milky Way is just how high of a percentage of its total mass is in the form of dark matter. Now, when I talk about dark matter, I'm not talking about ordinary matter made up of protons, neutrons, and electrons that's simply not able to be visible. We're referring to what's called exotic dark matter, matter that's made up of fundamental particles that do not strongly interact with light. Neutrinos would be an example of that. In fact, most astronomers believe that probably the dominant component of the Milky Way galaxy would be axions. They have yet to be discovered as individual particles, but that's kind of the current consensus. The Milky Way also stands alone in that it has such a small disk. Um, its disk scale length is just 98,000 light years compared to the Andromeda galaxy that's twice as long, 199,000 light years. And then the angular momentum in the disk is much smaller. And so for the Milky Way, it's 40% of what we see in large spiral galaxies, whereas Andromeda is exactly what we see in other large spiral galaxies. So the disk angular momentum of the Milky Way is just 40% of what we see in other spiral galaxies. And then when we look at what we call the outskirt stars, these are the stars that are more than 60,000 light years from the center of our galaxy. And we notice is they're all old, undisturbed stars. Whereas you look at the Andromeda galaxy and other spiral galaxies like it, we see that there's quite a mixture of old and young and middle-aged stars. And we see that the motions of these stars in the galaxies are highly disturbed, where those in our Milky Way galaxy have not been disturbed over billions of years. And this is what led to the discovery that our Milky Way galaxy has not absorbed a large dwarf galaxy over the past 10 billion years. It explains why the outskirt stars are all very old and undisturbed. It explains why the disk angular momentum is so low, because if we were to accrete a large dwarf galaxy, that would significantly add to the angular momentum of the Milky Way galaxy's disk. We don't see that. And the enigma here is a spiral galaxy cannot sustain its spiral structure for more than 3 or 4 rotations unless the galaxy is consuming or accreting or eating dwarf galaxies. But evidently, what's unique about the Milky Way galaxy, it's been regularly, continually consuming gas streams from other galaxies and small dwarf galaxies, but not consuming any large dwarf galaxies. Matter of fact, papers have just been published making the point that the Milky Way galaxy has gone 10 to 11 billion years without consuming any galaxies bigger than 1 billion times the mass of the sun in terms of its total mass. Not the case for the Andromeda galaxy. Just a half billion years ago, it did absorb a galaxy considerably more massive than a billion solar masses, and explains why the Andromeda galaxy has a warped spiral arm structure and why you see significant spiral arms long ways from the center of the Andromeda galaxy. I'll show you a high resolution image of the Andromeda galaxy in a little while. On the other hand, if the Milky Way galaxy wasn't consuming lots of tiny dwarf galaxies, it wouldn't be able to sustain its spiral structure. The reason why dwarf galaxies are dominated by dark matter and gas. They have a very low ratio of stars to total mass. And so when a large galaxy consumes a dwarf galaxy, there's this big infusion of gas, and it takes that big infusion of gas to sustain the spiral structure. Take away the accretion of gas, the spiral structure winds up, collapses, excuse me, and transforms our spiral galaxy into a highly condensed ellipsoidal galaxy. And if that were to happen, life of any kind would be impossible in our galaxy. The stars would simply be too close together, and the stars would be too close to the supermassive black hole that would exist at the center of such a galaxy. Incidentally, all galaxies have supermassive black holes in their nuclear cores. We define a supermassive black hole as a black hole with more than 1 million times the mass of our star, the sun. Excuse me. The Andromeda galaxy has a supermassive black hole a little more than 100 million times the mass of our star, the sun, which is typical for a galaxy of its size. By comparison, our Milky Way galaxy has a supermassive black hole that's only 4 million times the mass of our star, the Sun, a good factor of 30 times smaller than the black hole in the Andromeda galaxy. And that's one reason why advanced life is possible in our Milky Way galaxy. We have a tiny, supermassive black hole, and we happen to be far enough away from the center of the galaxy that the radiation coming out of it is not a problem for life. Incidentally, another fortuitous feature is that over the past million years, that supermassive black hole at the center of our galaxy has been an exceptionally quiet phase. It is absorbing objects like asteroids and comets, but nothing bigger, and consequently, the radiation coming out of the supermassive black hole doesn't do us any damage. It also helps that the sun orbits the center of our galaxy very much in the plane where there's a lot of dust that shields us from the radiation of the supermassive black hole. So these are just a few of the over 200 specially designed features of our Milky Way galaxy that makes it possible to be a home for advanced life. Now, the reason why our Milky Way galaxy is beginning a steady diet of gas streams and small dwarf galaxies to sustain its spiral structure without absorbing any big dwarf galaxies is because not too far away, we see the third and fifth largest dwarf galaxies in the local group. That is the Large Magellanic Cloud, which is below the Milky Way in this image. And then just to the right and below the Large Magellanic Cloud, we have the Small Magellanic Cloud. These two relatively large dwarf galaxies are just the right distance from our Milky Way galaxy and just the right angular position relative to our Milky Way galaxy and orientation with respect to one another that they actually act as a funnel where they funnel in gas streams and small dwarf galaxies into the core of our Milky Way galaxy, and which explains why, without consuming any big dwarf galaxies, our Milky Way galaxy has sustained its beautiful spiral structure for as long as it has. And this next slide, we zoom in. Incidentally, this is not a photo image of our Milky Way galaxy. There's no way we can send a satellite or rocket above our Milky Way galaxy and look down on it and take a photo. Rather, this is a reconstructed map where astronomers map different parts of our Milky Way galaxy at different wavelengths. At optical wavelengths, the dust in the plane of our galaxy blocks the view of many parts of the spiral arm structure, but at radio and X-ray and gamma ray wavelengths, you can see through a lot of that. And so by imaging our galaxy in different regions at different wavelengths, astronomers have been able to construct a detailed map of the structure of our galaxy. And one of the things that stands out right away is just how symmetrical are the spiral arms. It's a 4 spiral arm. You see 2 dominant spiral arms and then 2 smaller spiral arms that come up from the bar of our Milky Way galaxy. I won't go into the details, but advanced life is only possible in a spiral galaxy that has a central bar. And the central bar of our Milky Way galaxy is just the right size and just the right mass. That little yellow dot there shows you the position of the solar system, indicating that we're in between the Sagittarius and Perseus spiral arms. And we'll look in more detail at what's going on in the immediate solar neighborhood in subsequent slides. But this is what's special. Because we've only been consuming tiny dwarf galaxies and gas streams without consuming any of the medium or large-sized dwarf galaxies, our Milky Way galaxy has a spiral structure that's been undisturbed for the past 10 billion years. Moreover, we see that it's retained an incredible symmetry And if you look between the spiral arms, we see very few feathers and spurs. And now what I'm going to do is actually show you uh, the 16 spiral galaxies we astronomers have found. We've looked at tens of thousands of spiral galaxies that are in the relative vicinity of our Milky Way galaxy. These are the ones we can map in detail, many tens of thousands. I'm going to show you the 16 spiral galaxies that come the closest to matching the features of our Milky Way galaxy. So these are the best twins we have found. And the first one is the Andromeda Galaxy. It's called our sister galaxy because it's about the same total mass. But you notice that its spiral arms extend out much more so than our Milky Way galaxy. In fact, the outer spiral arms are quite dominant, whereas the outer spiral arms of our Milky Way galaxy are the feeblest of all the spiral arms in our galaxy. And you can see two dwarf galaxies below the Andromeda Galaxy and just above, a little bit to the left of the center of the Andromeda Galaxy. And it was a scholar who's part of our community, our scholar community, David Block in South Africa, member of our scholar community. Several years ago, he published a paper where he was able to demonstrate that that galaxy, dwarf galaxy you see above and to the left of the Andromeda Galaxy, passed through the spiral arms of the Andromeda Galaxy about a half billion years ago, severely warped the spiral arm structure and distorted the spiral arm structure as a result. This is common for large spiral galaxies. It hasn't happened to the Milky Way galaxy, but we don't see any other spiral galaxy of approximately the size of the Milky Way that has escaped such incidents. This is NGC 4526, and here you can see it's got these massive dust lanes. And again, you can see just how bright the center of that galaxy is, and just how tightly wound the spiral arms are. And then this is M100. This has often been referred to as the twin of the Milky Way galaxy. It's got a small barred feature, but not really, you have to really look hard to see the barred feature. But look at all the feathers and spurs between the spiral arms. So here again, you see evidence for significant disturbance of the spiral arm structure. Same thing is the case with NGC 3370, where literally you don't really see any black space between the spiral arms. And it's got rather tiny central bulge. Our galaxy's got a bigger central bulge, but here you just see that the arms are highly distorted and have an extremely high population of feathers and spurs between the arms. Here's the pinwheel galaxy. Here we do see that the spiral arms are not nearly as tightly wound as the previous galaxies, but once again, you can see lots of feathers and spurs between the galaxies, and you can see that the spiral arm structure is not symmetrical at all, that you actually see pieces of spurs joining one arm to another. Here's NGC 908, and you can see especially the outer spiral arms have been significantly distorted as a result of encounters with the galaxies. NGC 3344, a little more symmetry in the spiral arms, but you also notice the spiral arms are loaded with these gigantic, dense molecular clouds that are aggressively forming new stars. Every one of those pink spots is what we call a maternity ward, where new stars are forming, and they're big enough that it's distorting the spiral arm structure. And then we have M83, and here you see significant distortion. But again, I want to remind you, these are the 16 spiral galaxies that come the closest to matching the features of our Milky Way galaxy. The fact that this made the list, given the tremendous distortion you see in the spiral arm structure, again just emphasizes how special and unique our Milky Way galaxy is. NGC 4921, and it's hard to see anything in between the spiral arms, again, because of just how much spurs and feathering has been going on. And you can see even in the center of this galaxy, significant disturbance. This is NGC 1232. And here you can see that especially the outer arms, highly distorted. The symmetry is gone. A little bit of symmetry in the center, but even if you look closely at the center, you can see that even those arms, excuse me, are lacking in symmetry. A little more symmetry here in NGC 6384. This is actually one of 4 galaxies that astronomers identified as coming the closest to matching the features of our Milky Way galaxy. The size of its central bulge is about the same, but where the similarity ends, look at all the spurs and feathers between the spiral arms. And also you can see, as you look at the outer parts of the arms, significant distortion. UGC 6093 probably comes the closest of all to matching the Milky Way galaxy. Its barred feature is quite similar to what we see in our Milky Way galaxy. But even the arms that are close into the bulge of the galaxy show significant distortion, particularly off to the right. You can see that the arms are not symmetrical. Arms actually overlap. NGC 3992 is another galaxy that's been touted as coming the closest to matching our Milky Way galaxy. However, its bar is a whole lot bigger than the bar in our Milky Way galaxy. And again, you just see how many spurs and feathers exist, and particularly the outer arms show significant distortion. And then we got NGC 6744. It's a place where aggressive star formation is going on, and you can see how that aggressive star formation is distorting the spiral arm structure. And then last of all of the galaxies that are touted as coming the closest to matching our Milky Way galaxy is UGC 12158. But again, once you get past that central bulge, really significant spiral arm distortion. And hey, here's our Milky Way galaxy. And I think it's clear it really does stand apart from all these other galaxies that are touted as coming closest to matching the features of our Milky Way galaxy. Excuse me, I apologize. I'm an asthma sufferer, so I have to do that once in a while. But what I've done here is to collect a couple of montages. These are the 12 spiral galaxies that come the closest to matching the features of our Milky Way galaxy. Then contrast that with our Milky Way galaxy. And as I mentioned before, one of the big reasons why our Milky Way galaxy has such incredibly symmetrical spiral arms with very little spurs and feathers between the spiral arms is that we have this gigantic halo of exotic dark matter. And so that gray area shows the size of the halo. If you're looking down on the Milky Way galaxy and you see a gas disk, that's that light gray. That's another unique feature. The gas disk of our Milky Way galaxy is actually larger than the spiral arm disk, the one defined by the stars. And if you want a side view, or this is what it would look like, where you have this slightly flattened oblate spheroid of this dark matter halo, exotic dark matter halo. You got this thin disk of gas that's a little bit bigger than the stellar disk. Then you got the central bulge. And here again, we get to look at the stellar characteristics of our Milky Way galaxy. And what I'm going to do here is actually show you the latest map. This just got published a couple of months ago, an update of the constructed map of our Milky Way galaxy. And I'm going to zoom in really close to the spiral arm structure that's near our star, the sun. And what it reveals is that when you look at the Perseus arm and the Sagittarius arm, those are the two dominant arms of our Milky Way galaxy. And we're in between those two dominant arms. We're actually along a smaller arm that's referred to as a local arm, which basically splits off from the Perseus arm about 60 degrees back along that spiral arm. But because that we're located a certain distance from the center of the galaxy, the density of stars and molecular clouds that's closest to our sun in both the Sagittarius arm and the Perseus arm is at a minimum. And likewise, as you look at our local arm, the density of stars and gaseous nebulae and molecular clouds is at a minimum. Now, when you look carefully at this slide, you can see a pink spot just above and to the left of that thing that designates our sun. That's the Orion Nebula, and it's actually about 800 light years away. And so this is not a 3D image. It actually stands behind our sun to quite a degree in this particular slide. But the bottom line is there's no big star clusters, no giant molecular clouds, or any of these gaseous nebulae close enough to our sun to be a problem for advanced life. Okay, a couple more slides, and we're going to take your questions. One of the features of our Milky Way galaxy is that the abundance of elements heavier than hydrogen and helium varies with respect to the distance from the center of the galaxy. And so this little graph here shows you that variation. And that little dotted line there at about 4 kiloparsecs from the center of our galaxy, and we say, what on earth is a kiloparsec? It works out to 3,200 and 3,200 and 3,260 light years. That first dotted line at about 4 kiloparsecs shows you where our sun was born. It was actually born in the part of our galaxy where you got the highest abundance of elements heavier than hydrogen and helium, but it got ejected from its birth cluster and migrated all the way to that second dotted line at about 8 kiloparsecs from the center of our galaxy. And notice that's one of the minimal regions of metal abundance. And what this points out is that we were born in a place where we got super endowed with these heavy elements. And that's crucial for advanced life. Advanced life wouldn't be possible on planet Earth unless we were super endowed with iron, super endowed with copper, with uranium and thorium and selenium. Those are life essential elements, the selenium, the iron, the cobalt. And then also we need the uranium and thorium to be able to establish a strong magnetic field to protect us from deadly radiation and to actually set up plate tectonics, which leads to the formation of continents. And so this particular slide shows you where the sun was born and where it wound up. It was born in the most dangerous part of our galaxy and got ejected and settled down into the safest part of our galaxy. And that little red annulus you see there is the galactic habitable zone. That's that distance from the center of the galaxy where the spiral arm structure rotates at the same rate that a star under Newton's laws of motion would revolve around the center of the galaxy. And that's where you want to be, because if you're in that spot, you'll cross spiral arms much less frequently than if you were interior to that co-rotation distance or exterior to that co-rotation distance. Now, if you're exactly at that distance, you would experience mean motion resonances, which would kick you completely away. The sun happens to be just on the inside where it can remain in a stable position for billions of years, crossing a spiral arm only about once every billion years. Say, when did we last cross one? 500 million years ago. We're at the safest time right now. Well, if you want to read more about this, you can get The Creator and the Cosmos, 4th edition. We're giving away a free chapter at reasons.org/Ross. Chapter 15 we're giving away, and we're giving away chapter 14 of my latest book, Weathering Climate Change, at the same URL, reasons.org/Ross. That's also where you can go to get all the slides that I've been showing you. So I would encourage you to get those slides because they're all high res and you'll be able to look in detail and see the features that I was talking about. You can get those at reasons.org/Ross. /Ross. I'm going to take your questions now. Excuse me. And I'll take questions on any topic you want to raise. And so you can type in your questions and I will get to them. And let's see. Let me open up the Q&A box right now. Oh, okay. I see we got some questions coming in already. And so we're going to do this for a while. And then we're going to do a bonus feature for all the questions I don't get to in the next 30 minutes. We're going to actually have a bonus feature where we answer them by going to Reasons to Believe RTBLive Extra Podcasts. And you can get this by subscribing to Reasons to Believe podcasts from almost any podcast service. And that's where I'll be answering the questions I don't get to in the next 30 minutes. But the first question comes from Tom Jordan, and he asks, is there any truth of the evidence of a parallel universe based on the article, NASA may have uncovered evidence of bizarre parallel universe where physics, time operate in reverse? I've actually had to answer that question quite frequently on my Facebook and Twitter page. And yes, this did come out as a NASA announcement, and it's based on some measurements that have come from the telescopes at the South Pole that actually indicates there may be some subtle feature in the cosmic background radiation that might indicate an adjustment to the standard Big Bang creation model. However, if you actually read the one on the New Scientist site, which tends to be a little more nuanced, it's quite clear that the authors there are making a speculation on a measurement that's not yet been confirmed. As I've been explaining to people both on Facebook and Twitter, there's no peer-reviewed paper making this claim yet. Moreover, there's not even a preprint written by astronomers that's making this claim. All we have are web articles. And one thing I've been trying to communicate with our constituents, whenever you see a web article on some new scientific discovery or scientific claim, I wouldn't give it any credence until at least a preprint written by the scientists who are intent on trying to get this in a peer-reviewed journal shows up. And so people say, Hugh, are you going to comment on this? I will comment on it and write an article on it once there's some written paper by these astronomers making the claim. But what I can tell you right now is that it's a tentative claim based on a measurement that needs to be confirmed. But basically what these astronomers are saying is if what we think is happening in the maps of the cosmic background radiation is real, and we're not sure yet, but if it's real, it might indicate some bizarre physics. And a parallel universe is one of multiple possibilities. If you read the web articles, it gets the idea that the parallel universe is the only way to explain what's been observed. That's incorrect. There's multiple ways to explain the observation besides a parallel universe, but I do agree a parallel universe is one such possible explanation. And incidentally, many of the inflationary Big Bang creation models do predict that there's going to be many other space-time realms besides the one that we live in, our universe. So if we do find this is real, this would be right in line with standard Big Bang cosmology. And again, I want to remind all of you, the Bible said it first. The Bible was the first book in the hands of humanity that spoke about the universe having a space-time beginning, where the universe continuously expands from that space-time beginning under laws of physics that don't change, where one of those laws is a pervasive law of decay. Those are the four fundamental features of Big Bang cosmology. If we live in a universe that continuously expands under a pervasive law of decay, that's a universe that gets colder and colder in a highly predictable way, exactly what we see in our measurements. I'm impressed that the Bible made these statements thousands of years before astronomers even discovered that that was a possibility. Okay, by the way, there's an article on our website, uh, Big Bang, the Bible Said It First. So you can get that and read that for free. But another question we got here is from Tim Boyle, a friend of the ministry, part of our scholar community. He said, would the Magellanic Clouds be within the exotic dark matter halo? I presume he's talking about the dark matter halo of our Milky Way. Assuming so, how do they interact with that? Well, the Large Magellanic Cloud has a dark matter halo of its own. And yes, the Milky Way's exotic dark matter halo, being 1.9 million miles in diameter, encompasses both the large and small Magellanic Clouds. The Large Magellanic Cloud is only 162,000 light years away, so it's well inside the exotic dark matter. In fact, the dark matter halo of our Milky Way galaxy extends almost halfway to the Andromeda galaxy. The Andromeda galaxy also has a big halo, but nowhere near as big as the Milky Way galaxy. And how do they interact? Well, if they're interacting, basically what's happened is the large and small Magellanic Clouds for billions of years have been moving closer and closer to our Milky Way galaxy. Matter of fact, the Large Magellanic Cloud brought a whole lot of small dwarf galaxies with it. It had its own collection of dwarf galaxies, and our Milky Way galaxy has been stealing small dwarf galaxies away from the Large Magellanic Cloud. And again, that's important to sustain our spiral structure. What's going to happen in the future? Well, the Large Magellanic Cloud and the Small Magellanic Cloud with it are going to continue to move towards our Milky Way galaxy. And so Timothy is right, is that this halo is going to cause these galaxies to continue to move. And astronomers calculate that a little more than 4 billion years from now, the Large Magellanic Cloud will merge with our Milky Way galaxy. And when that merger event happens, there's going to be an enormous distortion of our spiral arm structure. Will the spiral arm structure survive? I think it will, but it's going to be extremely distorted. So you might take that into account when you're considering your future investments, that 4 billion years from now, there's going to be this major disturbance in the spiral arm structure of our Milky Way. Okay, question we got from Michael. He says, as the Milky Way galaxy consumes a dwarf galaxy, are the dwarf galaxy's heavy elements utilized for new star formation, which also plays a role in maintaining the spiral arm structure integrity? Well, he's right in the sense that you won't have spiral arms unless you got stars forming. Basically, the spiral arms in our Milky Way galaxy are the regions in our galaxy where new stars are forming. And those new stars form because we have gas from dwarf galaxies being distributed out from the core of our galaxy along the spiral arm structure, in what astronomers refer to as density waves. And so it's important to realize that spiral arm structure, it keeps getting updated as a result of gas being infused into the interior of our Milky Way galaxy. And then we got a question, what is keeping the arms of our Milky Way in such a good order? Is the absorption of dark matter to stabilize our galaxy a unique feature? Well, it is important that we have this gigantic halo of exotic dark matter. So that's a huge factor in stabilizing the symmetry and the structure of the disk of our Milky Way galaxy. It's also important that it be absorbing small, tiny dwarf galaxies, not big dwarf galaxies. And the fact that it has to do this, I mean, for example, if our Milky Way galaxy were to have an episode where it wasn't absorbing small dwarf galaxies, after about 3 revolutions of the spiral arm structure, the spiral arm structure would collapse. So it's important that it not only consume these small dwarf galaxies, but it do so on a regular basis. Kind of like us, we need to eat 3 meals a day. We start skipping meals or you go several days without meals, it's going to cause problems with our health. And so, but that's one of the unique features of our Milky Way galaxy is the regularity with which it's been consuming these small dwarf galaxies and gas streams without having any encounters with medium or large size dwarf galaxies. Okay, Timothy is back and he's asking, is it safe to assume that the black hole at the center of our Milky Way is also just right? What would be the impact if it were larger or smaller? Well, it is just right. And I wrote an article on this, 2 articles on this, by the way, that you can see in my blogs at reasons.org. My blog is called Today's New Reason to Believe. And if you look, just search under supermassive black hole, those 2 articles will pop up where I talk about the amazing design of our supermassive black hole. What would happen if it were larger? If it were larger, it would be accreting not just comets and asteroids, it'd be consuming larger bodies like brown dwarf stars and the big planets and maybe even stars. And when that happens, our supermassive black hole would spew out very deadly radiation. Wouldn't necessarily be the end of microbes on planet Earth, but it would be the end of us human beings. And so, fortunately, our supermassive black hole is small enough that that's not happening. So, what would happen if we had a smaller black hole? It's not possible for a galaxy that comes in at more than 1 trillion times the mass of our sun to have a smaller black hole. Our Milky Way galaxy has the smallest ratio on measure of the mass of its supermassive black hole to the total mass of its galaxy by at least a factor of 10. No other galaxy come anywhere near within that ratio that we see in our Milky Way galaxy. And if that wasn't the case, advanced life wouldn't be possible here. And again, I want to emphasize our Milky Way galaxy's supermassive black hole has not always been as quiet as it is right now. You go back a few million years, it was actually consuming more material, spewing out radiation. That wouldn't have been a problem for plants and for animals that don't live a long time or for microbes, but would have definitely been a problem for us. Say, why did God wait as long as he did to create us human beings on the face of the earth? One reason was he was waiting for this quiet period of our supermassive black hole. Incidentally, that quiet period is identical to the best possible time window for our sun, for supernova eruptions, and for a whole lot more. I got a whole chapter on that in weathering climate change. All these small windows of time that are essential to make possible our civilization on planet Earth, and how you got about 20 of these narrow time windows independent of one another, and they all happen to line up at the same time. So that to me is one of the strongest arguments that there has to be a supernatural, super intelligent being that designed our galaxy and all the components inside of our galaxy so it's possible for us to exist. Hey, Donald Carlson asks, how do you measure dark energy? Well, a lot of people said, why do you believe that the universe has, 6 times as much dark energy as it has ordinary matter, when you can't even find the particles? Well, we have found one set of the particles, namely the neutrinos. We found 3 different flavors of neutrinos, but obviously those neutrinos don't add up enough to explain 6 times as much exotic dark matter as the ordinary matter. Why we astronomers are so confident that this dark matter actually exists is that we can see the influence of its gravity. And so, yes, we can't see the predominant fundamental particles, at least not yet, but we do see the impact of the gravity of this exotic dark matter. Matter of fact, that gravity plays a crucial role in stabilizing the spiral structure of our Milky Way galaxy. Nick Tavani asks this question, does being in the local arm present any problem? I thought it's dangerous to be in a spiral arm. It is dangerous to be in a big spiral arm. It's even dangerous to be in like the local arm, which is kind of a small offshoot of the Perseus spiral arm. If indeed you're in a position along that arm where you got nearby giant molecular clouds, big gaseous nebulae, or star associations that are loaded with newborn big stars. So yeah, if you got O and B type stars in the vicinity, that would be bad news. Uh, the new book I'm working on, Interior Designs, I just finished a chapter where I make the point, if you look in the solar neighborhood of the local arm, there's not a single O-type star or B-type star. Those are the biggest stars. The next biggest stars are what we call A-type stars, and there's only four, within 30 light years of our sun. And the biggest of those four measures just 2 times the mass of our star, the sun. And so they're at no, they pose no risk to advanced life on planet Earth. And then if you look at the G-type stars, which are stars as big as our star, the sun, there's only 16 besides our sun that exists within 30 light years. All the rest of the stars are really small stars, and therefore don't pose a problem. And so we are in the best part of our local arm, and our local arm is in the best part relative to the Perseus arm and the Sagittarius arm. As I mentioned, the closest components of the Sagittarius and spiral arms are the least efficient or the most efficient in the supergiant stars and these giant molecular clouds. Okay, a question from Skip Carter. What about the warping or twisting in the plane seen recently in our galaxy? Well, this is a good point, Skip. Our galaxy does have a warp. The warp is caused by the gravitational interaction with a large Magellanic Cloud, but it's a small warp. And yes, there's a twisting of the plane if you go way far out. So if you go to the very edges of the disk of our galaxy, going out, say, 65,000 light years from the center, you do see where you get basically a twist below on one side and a twist above on the other side. But if you look at the maps, the degree of twisting is relatively small compared to what we see in other spiral galaxies, and especially the warp. Compare the warp of our Milky Way galaxy with the warp that you see and the twisting that you see in the Andromeda galaxy. Tremendous difference. And so that's one of the unique features of a Milky Way galaxy, is just how small its warp is and how small its twisting is, and the fact that the twisting is in a place far out from the center of our galaxy. And the spiral arms, unlike what we see in the spiral arms of other spiral galaxies, our spiral arms fade as you go out towards the distance from the center of our galaxy. Okay, from Dylan Carr. How would you respond to someone like Brian Greene, who says that we are just a product of the universe and ultimately do not have any free will? How would you try to persuade lay friends who agree? Well, I think Brian Greene had to exercise some free will just to write that statement. I mean, this is kind of what's happening amongst physicists and astronomers who take a non theistic perspective. If you take that perspective, you're basically promoting the worldview that physics and chemistry explain 100% of reality. And if you take that position, you can't tolerate the idea that we have a free will. And so there's a debate going on where people say, well, notice that we can do experiments on the brain where we throw an electric current and the individual's arm flies up or the leg kicks. Well, this is a reflex action. What you don't see is somebody putting in an electrical signal into the brain, and suddenly that individual gets motivated to write a 20-page paper. And therefore, well, again, to put this in context, I've got about 50 books in my office written by non theistic scientists trying to explain away free will and to try to explain away consciousness. But they all end up saying that, the consciousness in us human beings seems to be real. We really do seem to be conscious of what's going on around us, and we seem to make decisions accordingly. And yet they try to explain that through physics and chemistry. But every one of these 50 books I got ends up saying, we have no clue. And basically, I'm arguing they're really battling against the Christian worldview perspective that we human beings are dualistic. We're not just physical beings, we're spiritual beings. And it's our spirit nature that basically controls our brain. From a Christian worldview perspective, we can think of our brains as being, excuse me, we can think of our brains as being like a computer interface. And our spirit, our mind controls the brain. And the brain is basically that little physical computer like entity that allows our spirit to communicate with the physical world. And you say, what happens when the brain dies? Well, you no longer have the interface. And if you don't have the interface, that means that the spirit within us is not able to communicate with the physical world. But again, from a Christian worldview perspective, when we human beings die, we cease to be able to influence events in this physical world in the universe, but we continue to exist in the spiritual realm. And so I would argue that the fact that it really does seem like we've got free will and we feel a responsibility for free will decisions, we really are conscious beings with a theory of mind that this argues there's something going on in us human beings that can't be explained just by physics and chemistry. By the way, you'll see some responses to this, a little more detail that I put on my Facebook page. From Todd Fry, in several of your books, you use a term, surface of the universe, and that our universe is flat. Can you explain what these mean, and do they have anything to do with each other? Well, I'm going to explain this, but don't try to visualize it because it can't be done. I think a good analogy is to think of planet Earth. Planet Earth is a three-dimensional physical body, and we human beings live on the two-dimensional surface of the three-dimensional Earth. Likewise, all the stars and galaxies, all the matter and energy, and even all the space-time dimensionality is constrained to the three-dimensional surface of the four-dimensional universe. Everything is on the surface, and that surface expands. And so you say, well, where's the center? The center is in a place we can't access. Just like you can't go to the center of the earth with your automobile, our telescopes are not able to go back to that center. Everything's on the surface. We can see what's going on the surface, just like we can take airplanes and travel on the surface of the universe. So just boost everything up by one dimension. You say, what about the flat universe? Well, the universe could be like a four-dimensional sphere, or it could be like a four-dimensional saddle where the lines of space go to infinity, or it could be flat. But it's not three-dimensional flat. It's four-dimensional flat. And actually, it's more complicated than that because we now know there's 6 very tiny space dimensions that accompany the 3 large ones of length, width, and height. And so we live literally in a 10-dimensional universe where all 9 of those space dimensions plus time expand from the cosmic creation event. But when gravity separates out, the 3 forces of physics, 6 of the 9 space dimensions stop expanding. They're no bigger than what they were when the universe was a 10 millionth of a trillionth of a trillionth of a trillionth of a second old. If you want to see details on this, go to The Creator and the Cosmos, 4th edition. I got a whole chapter talking about the geometry of the universe. Okay, a question here from Chong. He says, one may argue, even if our galaxy is like no other, it doesn't imply that it is by design. There's only one lotto winner, but it doesn't mean the winner is divinely chosen. Can you comment on it? This is often an argument against the idea that there's a benevolent, intelligent, supernatural creator that's responsible for the design. Basically saying, well, look at the size of the universe. There's 200 billion galaxies. You haven't looked at all of them in detail. Maybe there's one we haven't found yet that could be like ours, or maybe ours is just like this by pure chance. Incidentally, I don't think we're ever going to find a galaxy like ours because as we look farther away, we're looking farther back in time. You look farther back in time, the galaxies have not developed enough yet to become galaxies like ours. So, in that sense, we astronomers have really done an exhaustive search. But the whole point that's being missed here is you know, you need to evaluate the design by purpose. If we can't see any purpose in the design, I think you could argue, well, maybe this is just an accidental outcome of the operation of the laws of physics and the chemistry of the universe. But if we see specified purpose for the design, that argues that there's a mind behind it. And particularly if we see that the fine tuning design is dramatically greater as you focus in on more specified purpose. So it's one thing you'll see on our website. You can go to reasons.org/fine tuning. That'll pop up for you a 300-page compendium that I developed more than a decade ago. And what I've done there is to show you the level of fine tuning design to get bacteria that can exist in the universe for 100 days or less. And then I have another calculation of the fine tuning design we see to get microbes that exist in an ecology of microbes, not just one species, for over 1 billion years. And there you see how the fine tuning design evidence exponentially is greater than it is to get a single bacterial species for a short period of time. Then I got another demonstration of what it takes to get plants and animals. And there again, we see an exponential increase in the fine tuning design. And then there's one, what do you need to get human beings? And that's where you see the greatest growth in the fine tuning design of all, is when you go from what is needed to get plants and animals to what is needed to get human beings. And you won't see this in the compendium, but it is in Improbable Planet and also in Weathering Climate Change. If you put the fine tuning design in the context of what's needed for billions of human beings to exist, to thrive, to develop the civilization where the good news of salvation through Jesus Christ can go through all the people groups of the world so that billions of human beings can be redeemed from their sin and their evil in just thousands of years and not millions of years. This is where you see the greatest fine tuning design evidence of all. And based on what I've been researching the past 3 years, it really does appear that every component of the universe, Earth and Earth's life, and every event in the universe, Earth and Earth's life, plays a significant role in making possible the redemption of billions of human beings in a relatively short period of time from their sin and evil. And there's really no other way around that than that there's a God behind it all who has used his supernatural power and knowledge and intellect to design a universe in such a way that billions of spiritual beings can be redeemed from their sin and evil, while at the same time their free will capability to experience and express love gets magnified. So the fact that every possible design points in that direction, every feature we study of the events and components of the universe, Earth, and Earth's life is in that direction, tells us this is no cosmic accident. There's a mind behind it all that's making this possible. Okay, we got time for a couple more questions. This one is from John Robb. Oh, pardon me, I guess I already answered that one. Michael Marag. Is dark matter equal to the ether or energy grid that Nikola Tesla described and apparently extracted energy from it? The answer to that is no. What Nikola Tesla was trying to do was draw energy out of the magnetic field of the Earth. The Earth has a magnetic field of almost 1 Gauss, and he spent the latter part of his life trying to find ways to actually capture that energy in such a way as to generate electricity. And there is a lot of energy in Earth's magnetic field, but trying to capture it in a way to get any significant flow of energy to power our factories, cars, etc., is not possible. People have given up on that many decades ago. You really need much stronger, more compact magnetic fields to be able to make that happen. Okay, we got a question from Danny Barilli. Says, does our dark matter halo reach out to the Andromeda Galaxy? The Andromeda Galaxy is 2.5 million light years away. The dark matter halo of our Milky Way galaxy has a diameter of 1.9 million light years, which means its radius is 950,000 light years. So no, it does not reach out to the Andromeda Galaxy. It falls quite a bit short of the Andromeda Galaxy. The dark matter halo of our galaxy does not overlap the dark matter halo of the Andromeda Galaxy. Okay, we got a question, last question from John Robb. It says, Hugh, based on these findings concerning our galaxy and beyond, how do you conceive of heaven and hell? Very good question to end on. Thank you, John. And when you read the Bible, it tells us that a day will come after God has completed bringing to redemption the full number of human beings he intends to redeem, Romans 8:23, that when that happens, no longer will God need a universe with a pervasive law of decay. And when that happens, as God spoke the universe into existence, he will speak it out of existence. If you go through the entire Old New Testament, you'll find over a dozen passages that tell us that the stars that we see in the universe one day will no longer be. The universe will no longer be. God tells us in Genesis 1 that when he created the universe and all of its life, it was very good. It was the best possible universe to bring about the eradication of evil and suffering, while God simultaneously enhances the free will capability of us human beings to experience and express love. But it's not the ultimate creation. Unique to the Bible, it's a two creation model. God creates the universe to be a tool to eradicate evil and suffering, but once that happens, God takes redeemed humans into a new creation. If you read Revelation 21, it's radically new. Gravity doesn't exist there. Thermodynamics doesn't exist there. There is no death. There is no electromagnetism. The dimensions are different. What we notice is once the universe no longer exists, heaven survives and hell survives. So heaven and hell are not part of the space-time dimensionality of our universe based on what the Bible declares. The one pushback I've seen in that is that Jesus referred to hell as being below and heaven as being above. But I think he was talking about below and above in dimensions distinct from length, width, and height. After all, you can think of two-dimensional beings in a flatland universe, and if we were to tell them, hey, I'm above you, they would think you're in length and width because they would have no conception of the dimension of height. So I think that's what Jesus was referring to when he made references to hell being below and heaven being above. And likewise, similar texts that you see in the Old Testament. The very fact that heaven and hell survive, the elimination of the universe, tells us they're not part of the universe. They continue, the universe does not. Okay, with that, we're going to end our time with RTBLive. I do want to let you know that we're going to do an RTBLive extra podcast for the questions we didn't get to. And you can get that at any podcast service at Reasons to Believe podcasts. Next week, got a special treat for you. We're going to be bringing two of our scholars on board for RTBLive. We're going to have AJ Roberts and Jeanette Roberts. She's our virologist and molecular biologist. And Mark Clark, who's a professor of strategic studies at Cal State University, San Bernardino. I can't tell you how many dozens of students he's trained for our national security agencies in Washington. And Mark is an expert on conspiracy theories. And so next week, AJ Roberts and Mark Clark are going to talk about the origins of the SARS-2 virus that's responsible for COVID-19 and all the conspiracy theories that are running around about where did this virus come from and how should Christians think about this and how should we be thinking about this in terms of what inevitably will be other viruses that come our way down the road, and how do we discern whether or not some theory is a credible conspiracy or not. So that'll be next week at RTB Live, and so look for that. And I want to say goodbye to all of you. It's been a special treat engaging you with this new material. And hopefully I'll be able to develop a more polished message here on a galaxy like no other. Thank you and goodbye.